Okay, so this is the second of the Lewis structure videos. The first time we went over the basics of drawing Lewis structures, and we kind of went step by step, and we included a bunch of intermediate steps that we can get rid of as we get more and more comfortable drawing Lewis structures. So this is kind of the next level of Lewis structure drawing. And I'm just going to review very quickly what I already went over in the live help classes from yesterday. Basically, you're going to take the least electronegative atom and you're going to put it as the central atom. You're going to draw a single bond to each atom connected to the central atom. So one of the problems you needed to do on the assignment that was due last night was that you needed to do the thiocyanate ion, which has the formula SCN, and it's an anion, so it's SCN minus. And so if we wanted to find the least electronegative atom in thiocyanate, you've got the choices of S, C, and N. And as we discussed yesterday, it's going to be the carbon. Carbon is going to be the furthest to the left in the top row of the periodic table. It's the least electronegative atom. In general, carbon's a good choice for a central atom because it tends to be less electronegative than almost any other atom you're going to find in a structure. Okay. So there is the structure with the central carbon in the center and the other two atoms connected to it with single bonds. Obviously, we're not done. We're just getting started. The next thing we need to do is we need to check the electron count. The total electron in the structure must match the sum of the valence electrons for all the atoms, and then we're going to make an adjustment for the charge if it's an ion. In this case, it's a negative ion, so we're going to add 1 electron. So there's a little bit of the budgeting. We had 4 valence electrons for carbon, 5 for nitrogen, 6 for sulfur, that's 15, and we're going to add 1 more for the negative charge, giving us a total of 16 electrons. Okay. So now you're going to add electron pairs around each external atom until they all have full octets, or the supply of valence electrons is exhausted. So if we do that here, we've got 4 electrons in the structure. If we add 3 more electron pairs around each one of these external atoms here, then we would basically have a complete octet. And that's what I've represented here. And we can verify that we've used up all of the electrons, right? 2, 4, 6, 8, 2, 4, 6, 8. 2 complete octets is indeed 16 electrons. And so we're done. That has all the electrons we are going to put in a Lewis structure. But of course, we're not done yet because in order to have a valid Lewis structure, you have to satisfy the octet rule. We made sure it was satisfied to the external atoms, but we haven't satisfied it for the carbon yet. And a quick glance tells us it's certainly not satisfied. That carbon only has 4 electrons around it with those 2 bonded pairs. So, if you happen to be in a situation where you had extra valence electrons that were still left over at this point, you'd have to put them on the central atom because by definition, if you've gotten to this point, all the external electrons have full octets. That's not the case here, but that is a step that you might sometimes have to do. The ozone example that we did yesterday in the help class was an example of that, where we had to put a lone pair on the central atom. Okay, so what do we have to do to get this to be the right structure? Well, since the octet rule is not satisfied for all the atoms, we're going to convert lone pairs into bonded pairs until every atom has an octet. Okay, and so here I'm going to take one of my lone pairs off the sulfur and one of the lone pairs off the nitrogen, and I'm going to move those electrons in so they're between the sulfur and the carbon and between the nitrogen and the carbon to get this structure here. And so that is certainly a valid Lewis structure for the thiocyanate ion. It has the right number of valence electrons, 16, and every atom has an octet. Okay, so is that the only structure? In order to assess that, we have to draw resonance structures. So this is how you reflect electronic resonance using the Lewis structure formalism. When you are given more than one valid Lewis structure that can be drawn for a given arrangement of atoms, you need to account for electronic resonance. So what that means is you can have Lewis structures where there's more than one way to choose positions of multiple bonds and lone pairs for the given structure. So if you have a Lewis structure like that, you can use curved arrows to show how the positions of multiple bonds and lone pairs can be exchanged to generate another valid Lewis structure. And again, I'm going quickly here because this should all be review of the help class from yesterday. So there's the structure we just drew for thiocyanate, and what we notice is that we could take this lone pair here and move it in. That's what that curved arrow is showing. And we can take this bonded pair here and move it out. And in that case, we're still going to have the same number of electrons around the carbon. They're just going to be arranged differently. We're going to redraw them, okay, so that now we see we have a triple bond between the carbon and the sulfur and a single bond between the carbon and the nitrogen. The octet rule is still satisfied for all the atoms, and we haven't changed the number of valence electrons, so that's still a valid Lewis structure. Okay, we put the double-headed arrow in between to show those two things are in resonance. You're then going to repeat that process to include any other valid Lewis structures that can be drawn. In this case, we can have the electrons go the other way from the starting structure, where the nitrogen lone pair moves in to make a triple bond, and this bonded pair comes out to make a lone pair, and that would give us the structure that we've drawn here. Again, you should verify for yourself that the octet rule is satisfied for all the atoms. So these should be the structures that you included with the assignment that you submitted last night. Those are the 3 valid resonance structures for the thiocyanate ion. Okay, so in this case, unlike the examples we've seen previously, you actually have your double bond choices about double bonds and lone pairs being made around different atoms. So you wouldn't necessarily expect that each one of these represented an equivalently good choice for arrangements of multiple bonds and lone pairs. And in fact, that's right. One of these is going to be the best choice, meaning that it is the most stable or the lowest energy structure. So the way that we figure out which one that is using something called formal charges. So formal charges give us a method to do what I just talked about, find the best resonance structure. And they do this by assigning a value called formal charge to each atom in the Lewis structure. And we're going to do that by comparing the number of valence electrons in the free atom. In other words, the atom that we would think about on the periodic table. You look at nitrogen and say, oh, it has 5 valence electrons. And then we're going to have rules for how we assign the electrons around nitrogen in the structure to nitrogen. And so we have a number for the electrons in the structure. We're going to compare that to the number of valence electrons normally expected for a nitrogen atom. If the number's the same, the formal charge will be 0. Okay. Otherwise, it's going to be the difference between those two, with the number being getting a positive charge for the formal charge if there are fewer electrons in the structure than in the free atom, and a negative charge if the other case applies. Okay, so each atom in the structure gets the electrons for each lone pair it has, and 1 electron from each covalent bond connected to it. That's how we get the number of electrons assigned to a given atom in the Lewis structure. And there's a very simple formula for this. The formula for the formal charge is just going to be the number of valence electrons. So for nitrogen, again, that would be 5. And then we're going to look at the structure, and we're going to see how many lone pairs there are, and we're going to count all the electrons in those lone pairs. That's going to be 2 times the number of lone pairs. And then we're going to get 1 of the electrons in each covalent bond, so we can just count the number of covalent bonds. We're going to subtract all of that from the number of valence electrons in the free atom, and that will give us our formal charge. It's probably easiest to look at an example to understand this. Here's that thiocyanate structure. And so if we look at this, we can look at the carbon. Carbon has 4 valence electrons. In this structure, okay, it only has 4 bonds connected to it, 4 covalent bonds connected to it, and no lone pairs. So plugging into this formula, we would subtract 4 for each of the covalent bonds, and that would mean we'd get 0. The number of valence electrons in both is the same. For sulfur, if we do the same thing, sulfur is right below oxygen on the periodic table. It has 6 valence electrons. We have 2 lone pairs here, so that's going to account for 4 electrons in the structure. And then there's 2 covalent bonds, that's 2 more, so that's also 6. So again, we are going to see a formal charge of 0 for the sulfur. If we now go to the nitrogen, nitrogen has 5 electrons, 5 valence electrons. In the structure, there's 2 lone pairs around it, so that's 4, and then there's 2 covalent bonds, so that's 2 more. So that means there's 6 electrons assigned to nitrogen in the structure, and when we subtract that, we're going to get a formal charge of -1. Okay, so this is how formal charges actually work. And then we have some additional rules that we can use to figure out which of those 3 resonance structures we drew is actually the best one. Okay, so formal charges give us that method that we were talking about. And so the first rule with formal charges is that the total of all formal charges must sum to the overall charge on the species. It's obviously going to be 0 if it's a molecule. Molecules don't have charges. Or if you have an ion, it's going to sum to the charge. In the case of the thiocyanate ion, it should have a -1 charge, and you'll notice that if you add up those formal charges, it adds up to -1. So that works quite well. The best structure is the one where each formal charge is as close to 0 as possible. Obviously, in a molecule, the best case would be where every single atom has a 0 formal charge, and that's often the case for molecule structures. If you have a structure of an ion, that can't be the case because we're going to have a charge somewhere, or we're never going to be able to add up to an overall charge. Okay, so in that case, or in another case where you have non-zero formal charges, the best structure puts the negative charges on the most electronegative atoms. If you think about the property of electronegativity, that makes sense. Something like electronegative wants to have more electrons. So if you're going to have an extra electron in the structure, it makes sense to put it on the most electronegative atom. And similarly, if you have a positive charge in the structure, it makes sense to put that on the least electronegative atom. So let's go ahead and we will now assign formal charges for the other resonance structures. So we had this resonance structure where we had the triple bond between carbon and sulfur, and a single bond with 3 lone pairs around the nitrogen. So again, the carbon has 4 bonds around it, no lone pairs. The formal charge there is going to be 0. I would like you guys to pause the video and assign formal charges to the sulfur and the nitrogen. Okay, so if we go through, we're going to see that we get 0 for the carbon. The sulfur has 3 bonds and 1 lone pair for 5, but since sulfur normally gets 6 valence electrons, that means it's actually short an electron in the Lewis structure, so we're going to give it a formal charge of +1. The nitrogen in this case actually has 3 lone pairs around it, so that's 6 electrons, plus 1 more for the bond, that's 7. So there's 7 electrons assigned to it when it normally only gets 5, so it's with a -2. So clearly, using the rules that we've just discussed over here, this Lewis structure, this resonance structure, is not nearly as good as the one up here, which obeys that primary rule of trying to get each formal charge as close to 0 as possible. Okay, what about the other Lewis structure that we drew? Like this. So now we've got the triple bond with a nitrogen and the single bond with a sulfur. Take a minute and assign the formal charges for this Lewis structure. Okay, you should have assigned a 0 for the carbon. If we look at the nitrogen, we have 3 bonds and 1 lone pair. That's 5. Okay, so now the nitrogen has a 0 charge, and it's the sulfur that gets a -1 charge because we've got sulfur. There's 3 lone pairs for 6, and it's a covalent bond is 1 more, so that's -1. Okay, so in this case, now we have to decide, is this the best structure or is the one with 2 double bonds the best structure? And so the only difference between those is where we chose to put that negative sign. In this case, it's on the nitrogen, and over here it's on the sulfur. And if you remember, our general rule is that if we compare both of these atoms are sort of one space removed from oxygen. Nitrogen is 1 to the left, so it's going to be less electronegative than oxygen, and sulfur is a row down from oxygen. It's going to be less electronegative than oxygen using our rules for periodic trends, but when you go down a row, the drop in electronegativity is bigger than when you're moving adjacently in the same row. So that means nitrogen is going to have a higher electronegativity than sulfur, so that makes it a better place to put the formal charge of -1. So that means that this one with the 2 double bonds is going to end up being our best Lewis structure. This one would be second best because it still has the formal charges as close to 0 as possible, and then the bottom one is the worst. And what that means is that in the structure, remember I said that the real molecule doesn't actually move the electrons around like this. When you have structures that have sort of different goodnesses, like this one's bad, this one's the best, and this one's in the middle, what that means is that the actual way this behaves will be more reflective of the best, most stable Lewis structure and less reflective of the ones that are less stable. Okay, that's it.